which will be given by Bryan. The title is Genus Zero Maps, Quivers, and Bott Periodicity.
All right, well, thank you. Thanks for the invitation. It's been a really terrific conference so far. I really enjoyed all the talks, a lot of great talks. So this is joint work with Ravi Vakil and Balish Elik, and it's well, so at the risk of going against my own personal brand, there's not going to be any Claviau threefolds or any formulas involving modular forms or long complicated formulas. In fact, it's actually quite gentle, which I think is maybe a good thing on a beautiful day like this towards the end of the day. It's actually something, although you'll recognize a lot of the things that come up, as people have been doing enumerative geometry for 30 years, this is something that could really be well before enumerative geometry, something really that could have been done in the 90s. So let me start off telling you what I'm thinking about here. So let's begin by fix some coordinates, fix P1 with coordinates. So I really want to, so the point at infinity is this one, so I have an affine coordinate z. Okay, so in concrete, and I want to let x with a point be a variety with a base point, with a chosen point. And let's define an algebraic double loop space as follows. Very simple thing. We'll call it d-alg. This is going to be of x, this thing. This is going to be maps from this parameterized P1. So I'm really parameterizing this P1 to x. We'll say of degree d. So, by degree d, maybe I really mean like a homology class, but often just refer to it as a degree, and taking this point at infinity to the base point. Okay, so maybe this is really element of h lower to x as we do in Gromov theory. So, this space, I've given it a different name. It's, of course, really sort of different than the ones we're used to in Gromov-Witten theory because I'm fixing this P1 right here. And of course, if we look at the complex numbers and we think about this in the analytic topology, when we're over C, maybe, then of course P1 is homeomorphic to the two-sphere, and so I can think of this as an algebraic. So that first of all, there's a natural inclusion into the topological loop 2 space, right? So this algebraic space includes into the space that topologists might understand. So I'll put that as top x, this topological space of based continuous maps, of continuous based maps from the two-sphere. So this is, of course, the thing that the topologists study. And, in the spirit that a continuous function can be approximated by, a polynomial of high enough degree, we have the following sort of slogan or expectation. I don't really know what to call it exactly. Let's say just this following expectation. I'm still missing something, aren't I?
No, it's great.
For certain spaces, so this, I guess the word certain is going to be doing some work here, but anyway, for certain spaces or varieties X, I is a homotopy approximation. for homotopy approximation for D large. So D being large in some suitable sense. What do I mean by a homotopy approximation? So I induces, so i.e., I induces isomorphisms on pi k for all k less than some bound that depends on D, and this bound goes to infinity as D gets larger and larger. So okay, so I mean, I'm going to use this term homotopy approximation, which to mean this. You could also say this is just like a highly connected, topologists would say this is a highly connected map. And yeah, so of course this isn't going to be true for varieties in general, since there might not be any genus zero maps, but maybe for some good spaces, these algebraic spaces will be like homotopy approximations to the things the topologists study. And so in fact, the starting point here is really an old theorem well, it goes back to work of Kirwan and followed up by Siegel and Mann Milgram. And this is work back from the 90s. So the above expectation holds when X is a generalized flag manifold. So G mod P, reductive group by a parabolic, so generalized flag manifold. So I think the history here is that Kirwan studied this for the case, of course, Pn. You might think when are maps Pn approximate the continuous ones. And then Siegel did Grassmannians and Mann and Milgram did the general case. And moreover, I won't write it down, but you can get very explicit for these bounds. Okay, that'll be a little bit important for us so that you can actually write down what these bounds are. So obviously, let me, I think probably we all know this from our graduate school days, but let me just remind us that, this loop 2 in topology, plays an important role in topology, obviously. And let me give you some examples, namely Bott periodicity. For example, periodicity. So let me. Where do I want to state this? Periodicity. Let me put this over here. So I can phrase sort of classical Bott periodicity in terms of double loop spaces. So if let me use some notation. Well, U will be the limit as n. This is as topological spaces now of un. So this is just going back to some topology. These are, of course, just the unitary groups I want they include. I can take some limit, and I'm going to use that same notation for some of the other groups. Etc. And so the one way to phrase Bott periodicity, maybe not in its most general form, but one way to state it so there's two versions here. There's sort of the twofold or complex Bott periodicity, which you could phrase like this, although I'm not really saying abuse, but D top BU is homotopy equivalent to BU. And there's also the eightfold slash orthogonal periodicity. And I can state these in 4 equivalences of double loop spaces. So the way they go is, I'll keep writing this top, SP mod U is homotopy equivalent to BO. Fiddle 4, loop 2, D, top, BO. So now I'm iterating, right? So what's periodic here is, of course, if I apply loop 2 to BU, I get back to itself. If I apply loop 2 to SP mod U, I get BO. If I then apply that to BO, I get something that's homotopy equivalent to O mod U. And if I keep going, let me just record these here. This is homotopy equivalent to BSP. I get back to where I started, SPU. So this is homotopy equivalent. So here I'm over. This is statements purely in this sort of topological category, and I'm interested in things up to homotopy there. And what sort of, particularly now, if I apply this to homotopy groups of those spaces, this will say that that BU or U has 2 periodic homotopy groups, and then O has 8-fold periodic homotopy groups. So, okay, back to algebraic geometry. What's the goal here? I have these algebraic spaces, which in good settings give me approximations to these topological spaces, and I want to revisit these guys that were studied in the 90s and find good algebraic descriptions of them, in particular quiver descriptions, in a way that's going to give me theorems in algebraic geometry, which then recover these Bott periodicity statements. So let me say the goal. Don't like that chalk. So the overall project is to give quiver descriptions of these algebraic loop 2 spaces of generalized quiver or generalized flag varieties. And use this description to give algebrogeometric refinements of Bott periodicity. So what do I mean? Again, statements in algebraic geometry that when I go to the complex numbers, and then I go to the analytic topology, and I apply these approximations, I actually recover Bott periodicity. So some sort of finer statement that recovers Bott periodicity. Okay, maybe I'll leave the definition of that guy. Okay, so let me give the first example here. So first example. Oops. Let's take X to be the Grassmannian of n-dimensional quotients inside of n plus capital n-dimensional space. So this, to use this language of homotopy approximation, this is homotopy approximate to BU n as n gets large. Right, familiar thing that we can get any bundle of rank n by going to sufficiently large Grassmannian. And so let's now study this algebraic loop space. So let me fix some vector spaces. Fix U and W to be fixed vector spaces. Of dimension little n and capital N respectively. And let me introduce some mild notation that I'll use a couple times. So let's let U underline be the trivial vector bundle on P1 whose fibers are isomorphic to this vector space, yeah. So, and same with obviously W. This is not an isomorphic, this is a definition. And then, what by definition is this space up here? So then, -2 d alg of this Grassmannian what is this parameterized? So the points inside of here, if I have a map to this Grassmannian, that will give me a quotient of this fixed vector bundle, right? So this parameterizes surjections onto a rank n vector bundle. So E is a rank n, and it turns out degree D, the D here is given by the degree of this E, degree D vector bundle on P1. And the based condition tells me that at infinity, the fibers here are isomorphic to this U, right? So if I give the names to these maps here, we have that theta W at P infinity is 0. Okay, it's a pretty concrete thing. And so here's a quiver description of that space. Maybe I'll put it here. So let's let A be a vector space of dimension D. And, well, V is a space coming from a quiver representation. So let me just write it out a little explicitly here, but then I'll put it in a way that we all like to visualize it. And these tiny pieces of chalk. Okay. And so then, the space is it's the stable locus of the action of GLA. So GLA, of course, acts on this. And I want the stable locus, and it's exactly this guy. So it's the, it's quiver representations of this thing. So if this is the vector space A, I'm going to call this alpha, and I've got gamma from a vector space W, and I've got what I'll call a J to a vector space U, and GLA acts on this, and this is the stable. So let me give you a way to think about this. Absorb it for a second. This piece right here, what is this piece parameterized? So let me, right, so, the vector space A, along with alpha and J, determines this part, U to E, right? So I've got this, these are the things that I'm parameterizing. So in particular, I'm parameterizing sort of two maps from this fixed bundle to this variant thing. And the theta U is determined by this part of the quiver right here. And I want to think about this, actually, let me give this a name. I'll just call this a Zariski framing. So what is that supposed to connote? So my bundle E is sort of framed at P infinity. It's isomorphic canonically to U by this guy in particular at infinity, but this surjection here is actually sort of trivializing this E on some Zariski open set containing infinity. So let me just call that Zariski framing, and let me show you how to think about this part of the quiver as giving rise to that data. You can, of course, make this, these two guys have the same rank, and so the quotient, so Q is zero-dimensional sheaf. And since this is an isomorphism at infinity, the sheaf is supported on the affine line, so supported on P1 minus P infinity, which I want to think of as spec of the affine coordinate. Remember that was, I called that Z. And so in particular, it's a finite dimensional module for this guy. And to give you a finite dimensional module, let's see, do I want to put this here? I need a vector space and the action of the Z. So that's the A and the alpha. In fact, I should say, right, this guy has degree, this has degree D, so this has length D. And so how do I recover that map? Well, Q is determined as a C of Z module by A and alpha. A is the underlying vector space, and alpha is the multiplication by Z. And then to get this whole thing, I need a J actually lives in the space of extensions, Q, right? And in order to get this, the rest of this, I need an extension of Q by this trivial guy. And to see that J lies in there, right, we just can use Sayre duality 0 U dual oh, I didn't tell you what A is, sorry. Oh, it's, yeah, no, I did. Okay. This guy is Q minus 2 dual, which is the same as H0 U dual tensor Q dual, these are all isomorphic, to U tensor A dual, right? Because maybe did I say this? A is H0Q, the underlying vector space of Q, right? And so, and this is now a homomorphism from A to U. All right, so, and I should also observe that if I tensor this sequence by -1, I also see that this is the same vector space, and use the long exact sequence, this is the same thing as H0 of E of -1. Okay, so you can see how pretty easily the that date of the quiver gives rise to this map, and then the other guy comes so this map factors, right? This vanishes at P infinity, vanishes at P infinity, so factors through a map from this, which I'll call gamma underline, to E twisted by -1. And this map is determined by its global sections. So it gives rise to a map on homology, but it's in fact determined by that. And the global sections here are this map gamma to A, right? The global sections of this are A. Okay, so that's very, so fairly simple stuff because we're doing bundles on B1. But so it's this is how you get that quiver for that Grossmeyer. All right, and this was my first example. Why? So let's show you how we would apply this to topology, right? So how do we apply this to topology? Maybe I'll come here. I want to save that, or I can put it up later. So, right, what is the theorem say? It says that this variety GR n plus n, this is isomorphic to that vector space, at least the stable points in that vector space mod GL A. And now, this by this Mann-Milgram, well, I guess in this case by Siegel's work, this is a homotopy approximation. With the topological loops for large D, yeah, that's what I mean when I say that, for top. And as we discussed, as the capital N gets large, this is a better and better homotopy approximation. So another homotopy approximation to topological loops. I'm going to have to move this board up, aren't I? Just a sec. On BUN. On the other hand, this is a vector space minus a closed set divided by a group. So the inclusion into the whole vector space here maps to BGLA, and A is dimension D, so this is a BGLD. And this is also a homotopy approximation where you can compute the bounds, because I'm taking, if you take a space and you throw on a space of high codimension, the inclusion will be highly connected, right? I'm really only changing the homotopy groups high up. So this is also a homotopy, and you can compute the dimension of the complement of the stable locus. So this is a homotopy approx. You can compute it in terms of the D and the N and the little n and the big N. And then this, of course, is just homotopic to BU, D. And so, in fact, what you get here is you get a homotopy approximation between loops to of degree d in BUN and BUD. And of course, if I let n, little n and little d go to infinity, I recover this complex Bott periodicity. But it's sort of a refinement of that. It is a refinement of that. Both on the topological level that you compute and also just on this algebraic level there. So that's kind of the paradigm, and that's for the complex. That's for the period 2 stuff. Yeah.
So I'm not familiar with the proofs of the comparison results that you said, but is this just sort of pushing the differential topology into those proofs?
Is what pushing the differential topology into those proofs?
I mean, the original, Bott's proof of periodicity. I mean, it's not this. This gives a different proof. But, is this proof simpler in some way, or?
Yeah. So right. So one could argue like, why do you want a new proof about periodicity? There's lots of proofs about periodicity. Or you can ask, maybe the question is like, what's the actual relation? Like, are we pushing for Bott's proof, which was had to do with? But see, that was really, he sort of thought in terms of loop 1, and for reasons that I think are well known to people who do like A1 homotopy theory. I just want to think about loop 2, not loop 1. And he was sort of using, his original proof involved piecewise geodesic loops and whatnot. So it feels pretty different. Yeah. Like I said, I'm not completely sure that the end goal is to reprove Bott periodicity, but to get sort of some of these refinements seem to be something that even the topologists are interested in. And anyway, it's just kind of fun to figure it out. So that's why I'm doing it. So let's do the let's do something more from this case. So the next thing I want to study, maybe I'll go back over here. Is let's look at, instead of Grassmannians, I'm going to look at Lagrangian Grassmannians. So this is something that already came up in Dragosh's talk earlier. And I'm going to do the Lagrangian Grassmannian, but sort of simultaneously what I'm doing would work for the isotropic orthogonal Grassmannian, which also nicely made an appearance in Martine's talk earlier. So let's let J be the standard symplectic form on, so U will continue to be a vector space of dimension n, so I can make U plus U dual is a vector space of dimension 2n, and it has a standard symplectic form on it, or orthogonal form. And I'm going to view these forms as isomorphisms with the vector space and its dual, right? So this goes to U plus U dual be the standard symplectic form, which is 0, and hopefully I've got everything in the right spots. So given by that guy, so that J dual equals minus J, and we should simultaneously keep in mind the case where this is a plus, so this is an orthogonal form, and then this is a plus. And let's let L GR N2N, which, so this is the Lagrangian Grassmannian, which if we write in sort of compact notation is SP2N mod UN, or if we're writing it algebraically, this is SP2NC, well, or whatever field, divided by a certain parabolic that contains this UN as a maximal compact. So this Lagrangian Grassmannian, right, parameterizes Lagrangian subs or quotients. Let B be the Lagrangian Grassmannian. Lagrangian subs slash quotients of u plus u dual. So there's a nice little exercise in linear algebra that's already been alluded to a couple times, I think came up again in Martin's talk, which is the following little exercise. That if I have a map, I'll use this to a space, to a vector space L, of course I can now also make a map from the dual by using the form. So this is J inverse composed with theta dual. And the exercise is that this, this is exact if and only if L is a Lagrangian quotient. Or, and if and only if, of course, this is a Lagrangian sub. Right, so this makes it very easy to write down sort of this. We can now try and write down the analog of, let's put it here maybe. So let's look at the algebraic loops now. Let's loss 2n. Okay, so points correspond to this. So the maps of P1 in there, of course, the bundle analog of that. So this is exact sequences of the following form. U plus U dual. And so if I call this guy using my sort of same notation to E, then this little lemma over here in that particular thing, that particular form of that, says that this map should be, I apologize for the excessive number of duals here, but minus U dual. This should be exact. E is dimension, so rank n, degree d. And again, at infinity, this thing should be standard so that this map from the dual guy, so the standard Lagrangian, the base point inside that thing will just be the copy of u, or the quotient to u. So I guess the sub is the u in my convention is that guy. So this should be 0. Okay, so what's the theorem here? So again, this has a quiver description. So now it's actually a smaller looking quiver. There's just this J and this alpha. But there's a new, so stable locus, and this is the orthogonal group acting on A. So A is a vector space of dimension D that comes equipped with a orthogonal, with an orthogonal structure, right? So where dimension of A is D, and it comes equipped with an isomorphism phi from A to A dual, satisfying phi dual is phi. And moreover, this alpha should be compatible with that, right? So it's the equation alpha dual phi is equal to phi alpha dual. Okay, so we started off with this. We're studying this thing where there's a symplectic form, and on this kind of universal bundle, this thing, it's going to be the same. This guy whose fibers are this H0 of E minus 1, I actually now get an orthogonal form. And if I had started with the maximal isotropic orthogonal Grassmannian, right? So instead of SP, I'd had O, so that the J has this positive sign, then I would got the same theorem, but now this would have been a symplectic vector space, and this would be a symplectic quotient. Okay, so this is theorem. And let's see how that leads to some Bott periodicity statements. So I guess I've got that up there. So we can redo this diagram, sort of, in this context. So as in the ordinary Grassmannian case, A is H0 of this E tensor minus 1. And the question, and so what I'd like to explain is where does the orthogonal structure come from? Orthogonal come from? Well, if I take this equation, if I take this exact sequence and I tensor it by minus 1, so of course this is just a whole bunch of copies of O minus 1 summed together. So this is a bundle on P1 that has no cohomology. So if I look at the long exact sequence in cohomology, what do we get? We get an isomorphism from H0 of this guy to H1 of E dual minus 1, which from Serre duality is isomorphic to H0 of E. Again, dual plus 1, tensor by minus 2, you get back to this guy, now dual. And so you have an isomorphism with A and A dual. Right, so this explains why they're isomorphic. Now, where is this sign coming from? I do want to, it's kind of a sort of cute to see where the sign change comes from. So I want to actually show you that here. Oh, no, you know what I did? I skipped. Sorry, I skipped. I was going to give you the Bott periodicity thing. All right, let me do that real quick. Right, so, okay, again, what does the theorem say? It says that this space of algebraic loops, or algebraic double loop space of this Lagrangian Grassmannian is isomorphic to some vector space, the stable locus in some vector space divided by orthogonal transformations of this A. And as I said before, this Lagrangian Grassmannian So is a generalized flag variety, so this is a homotopy approximation to the topological loops. And this thing, let me just rewrite it in sort of the topologist notation here. And by the same argument as before, you can see explicitly the closed set that you were throwing out here. So this is basically, this is homotopy approximate to just the quotient of the vector space by this group. So this is a homotopy approximation with BO A, so this guy is BOD, and this is this loop to SPN. So if you go and you look up here, you see that this is again a finite dimensional realization of this SP mod U is homotopy equivalent to BO, but you know, I've got the degree D here and the D there and the N there, and these two have the same homotopy groups up to a range that one can compute. So this is again some sort of algebraic refinement of that Bott periodicity statement. Okay. Yeah, so let me show you where this orthogonal forms. So why do we get, oh, and similarly again, if I could have started with O2n mod U, and I would have ended up with a BSP, and then that would have been this this third line right there would have given me that guy. Okay, so there's a, how do I see this, this orthogonal form, or what's a better way to think about this isomorphism that also will tell me about this compatibility up here. So whenever you have an exact sequence like this, so here's a fun little trick from homological algebra. If you have an exact sequence where the middle term is a direct sum, of course I can turn this into an acyclic double complex. And so star gives rise to an acyclic double complex. So let me put the maps in here. And this is really the origin of the sign change. This very simple little thing, which is when you pass from double complexes to associated, single complexes, there are signs you need to introduce, right? So the sign, that minus sign that's up there, when we go to this double complex to make this thing commute, becomes a plus. So here's the plus sign. And again, if I had started with a plus sign there, this would now be a minus sign. Now, what's nice about an acyclic double complex is if you do sort of the spectral sequence argument, it tells me that this complex up here is that this is a quasi-isomorphism between this complex and this complex. So, this gives rise to an isomorphism, well, in the derived category, but of the cohomology of this complex, which was just Q, my zero-dimensional sheaf, and this is an isomorphism, I'll call capital Phi, and so we've already seen this guy. This is Q. So what is this? Well, this complex is obtained from this complex by dualizing the complex, tensoring by -2, and shifting. So that's the Verdier dual complex, right? So this is an isomorphism between Q and its Verdier dual, okay? And moreover, what is the Verdier dual of phi itself is, well, I just dualize this whole thing, and what I see is that I get the exact same complex in this case, which is, so we get the exact same morphism, so this is the plus sign. And notice if I had started with a plus sign and this was a minus sign, this minus sign would have, under duality, would have jumped over to this other side, and I'd have to introduce a minus sign in order to get them to be the same morphism. So this is really the origin of turning the plus signs into minus signs and minus signs into plus signs, is this silly little thing of going from exact sequences to double complexes. And this, of course, once you apply global sections to this, it gives me this phi over here, right? These guys be the phi, so phi, I mean global sections really to the inverse of this guy. But it also tells me that, the alpha up there is the multiplication by z in this module. So this is really it's really a orthogonal module, if you want. So this is the commutation. This is the fact that this is isomorphisms as modules give you that thing right there. Okay, so I think it's a sunny day, so I think I will stop there. Thank you.
Questions?
I vaguely remember a paper of yours from the 90s, Bott Periodicity, that involved moduli spaces of instantons for the classical groups. And if I remember correctly, the ADHM quivers for those are the doublings of the ADHM, of the quivers that you wrote down here. Is there a
Yeah, thank you for the question. This is how Ravi dragged me into this, in fact. Yeah, so there we did reprove Bott periodicity, but the thing that felt like it was cheating was using a difficult analytic result of Cliff Taub's about instanton, the instantons being basically homotopy approximations to the space of all connections. So it's actually kind of a similar, there's a similar flavor there, but that was, in some sense, a difficult analytic result. And so we're sort of thinking about, the Bott periodicity, at least these two loops are really more about things on P1. But you're right that this quiver is basically that first theorem, which is about the Grassmannian, about bundles on P1 being given by quivers, that's really just more or less ADHM, or it's what you get from the Bailenson spectral sequence for P1 is basically just a very simple exact sequence. So yeah, that's kind of where this comes from. But yeah, the reason that I started pursuing it from this end was to avoid that analytic result. Yeah. I mean, in some sense, what's replacing that analytic result is this work of Mann and Milgram, but that's sort of a little bit more down to earth, I think. There's no analysis there.
I guess the homotopy equivalent construction is obviously the same as the one in Bott's original proof.
Yeah, well, like I said, the Bott's original proof is really for the loop 1 that they do. There's several proofs now, so it's probably worth trying to sort out the relation of these to the other proofs. But I also maybe would advocate thinking that this is also something, the main theorem is the thing that's purely in algebraic geometry that that works over other fields or even other rings, and it's just and happens to give you Bott periodicity. So it's some sort of algebraic refinement of that would be my perspective.
Right, but that proof gives you a specific homotopy equivalence, I guess.
Yeah.
Maybe should we care at all?
I think it's really hard to unpack that because the double loop being given as two. I mean, I haven't thought about it, I guess is the most honest answer, yeah.
Are there other algebraic proofs of algebraic geometry proof of?
Well, yeah, I mean, like the A1 homotopy theory people have a very specific way they think about it that's pretty sophisticated. Again, it's a little hard for me to tell whether this is the same as theirs or not. This is sort of much more, in my brain, down to earth. This is pretty down to earth, right? This is just like bundles on P1. But yeah, so we haven't really sorted out the relationship between the way the A1 homotopy people think about Bott periodicity and don't. And there's definitely, I mean, there is something smart to say, which maybe I don't really know how to say correctly, about there's really two different notions of loop one in A1 homotopy theory. So we're kind of brushing that aside by just dealing with sort of this loop two.
But here it seems that pseudo-ideal P1 is responsible for Bott periodicity.
Yeah, maybe. I don't know. Something.
Is it also the same in theory?
I guess I don't know.
Do you get something interesting if you plug in the realization? I mean, that the P1 becomes a circle, and it becomes more like.
Well, yeah, that's part of how that's part of that circle of ideas. So no, I don't know. I haven't really. I guess you could just do that, right? I mean, you lose these theorems about the homotopy approximation. So that's a good idea, but I don't. Yeah, I'm not sure how to go from there. So I mean, there's also, I should say that, this was just a couple examples of generalized flag manifolds. You can play, at least for all the classical flag, I don't know how to do the exceptional guys, but at least for all the classical flag manifolds, you can get similar sorts of quiver descriptions, although for some of them, like the full flag, for example, it's a little harder to understand the topology. There's some, in particular, the open set is sort of bigger. Yeah.
If you put the elliptic curve there, is there any stabilization?
Ooh.
Because the vector bundles on it's.
You want the maps of an elliptic curve in, or where do you want your
elliptic curve to things like that?
Yeah, I don't know.
The space is stable.
Stable. Okay.
Yeah.
Are there similar descriptions for unpointed maps?
Endpointed maps. Yeah, I mean, I guess you could think of this as being, because remember, I fixed the complex structure on P1, so this is kind of like three-pointed maps, right? I mean, if you wanted to phrase this in terms of Gromov-Witten theory, it's like three-pointed maps where I'm asking one of the points to go to a specific point and I'm not compactifying. But so if we add points, I don't think we're doing much besides.
I think the question.
Without the base point.
No.
Oh, unpointed, not endpointed. Okay, unpointed. Ah, right. Well, so now I think, yeah. So you still have the Bailenson exact sequence is maybe a best way to say it, but you don't get sort of the same. One of the things that base point does is it gives you a splitting, which leads to the sort of quiver. So it's a little less. It's a little less natural. I guess I think it's actually dividing by a different group. I don't know. I didn't try and write that down, but yeah, there's still this exact sequence you basically get from Bailenson. Yeah. Yeah. This. I mean, maybe I should have just said. I mean, let me just do this one thing, right? So back in the Grassmannian case, I said that this data right here is equivalent to giving you an E and giving you a surjection. And I expressed it in terms of an extension. That extension is not actually that useful. Maybe the most useful way to get your hands on E, and this is what's coming from the Bailenson spectral sequence, is that you've got a map, you have a very explicit map from bundles, which is a collection of -1s and a collection of O's, whose quotient is E, and this map right here is x0 minus alpha x1 j x1. So in this case, the alpha and the j give you a very explicit map from this bundle to this bundle, whose quotient is the E and whose projection is this thing. And this is sort of the analog of the ADHM. And if you don't have that base point, you don't have a splitting of this space. This is a different vector space here. I mean, this is you can't split an A off from A plus U. This is really secretly, this is H0 of E, and this is H0 of E minus 1 twisted by -1. Right? So without the base point, you still have this description. But you no longer get a splitting, which means you don't have quite as easy a way to write this map. I think that's really the difference. And so it's a little harder to get to quivers, maybe.
More questions? Okay, so let's take a speaker again.